We now come to another very important topic. What is the power and torque required to accelerate? Remember, first we have to overcome the gradient resistance if there is a gradient, but you typically never try to accelerate on a slope. So, that will not be relevant, but rolling resistance and the aerodynamic resistance, and then you have to add the acceleration power. Torque on the other hand will also be required during climb, even at a, because torque is independent of velocity. Is just force multiplied by the simply the wheel radius. Power has extra velocity component, force does not have. So, torque will become a problem, and we will be looking at the power, force and this. Typically, a vehicle is often defined when you go to purchase a vehicle, you see how much acceleration it gives. You typically ask, if I want to go to the maximum velocity, in how many seconds can I go to maximum velocity? When I start at 0, do I go to the final velocity V f in t seconds? T can be 10 seconds, 20 seconds, that often becomes a comparison between one vehicle and another. So, first that we will calculate what is the force required to go to the maximum velocity. So, let us first assume a linear acceleration, that the acceleration is constant, acceleration is a. So, velocity starts, acceleration is a, at time t it reaches the final velocity V f. What is the acceleration? The final velocity is V f and divided by t, time taken is t. So, that is the acceleration that is required, if it is a constant acceleration. So, what is the force? It is mass into the acceleration, which is V f by t. What is the acceleration distance? When it goes t seconds, what is the distance that will travel? And if you remember your formula, half f t square, s equal to u t plus half f t square, u was 0, the initial velocity was 0. So, half a t square, half a t square. What is the work done during acceleration? Well, force into distance, our old physics formula, and that comes to 0.5 m v square, 0.5 m v square. And what is the average acceleration power? Well, total work done divided by the time. So, it comes to half m v f square by t. Now, that is the average acceleration, but if you see that is the average acceleration, but when it is the maximum velocity, the velocity will be V f, at that time peak power requirement will be m v f square by t. So, it will be double the average, that is the power required at peak power required, because when the velocity is V f, it is m v f square by t, but that time it is actually V travelling at that speed. So, m v. So, leave the peak power. So, what we often sort of say, do I really need to accelerate linearly? Because power requirement always will have a extra v term. Force may be constant, power will have a v component. So, if force is constant, in the beginning my power requirement is small, in the end my power requirement is very large. That is the reason peak power requirement is m v f square by t. So, can I actually go faster, higher acceleration in the beginning? Why? Because my power requirement will be small, acceleration will be higher. So, but the velocity will be the force required will be higher, but the power requirement will be small, because velocity is small, and later on travel at lower velocity, lower acceleration. So, can I split it into a 1 and a 1 by 2? What happens to the power requirement, the average power requirement you will find if you do this, and I have given this problem in assignment number 1.2, where you will see that the peak power requirement goes down by 0.667%. If 50% of the time you travel at a speed a1 and the 50% of the time you travel at a speed a1 by 2 and you reach exactly Vf at time t. This is the problem that has been defined in assignment number 2. If you calculate it, you will find that the power requirement is at time t is 0.667 times what would have been the linear. But the average power will be same. In the beginning, you are going at a slightly higher acceleration. So, that time the power requirement is larger, later on you are going at lower acceleration. So, the average power requirement will depend on the total energy, and total energy will be given by these expressions. So, basically what I am pointing out that I need only 2/3 of the Vf by square by t. Out here I require only 2/3 of the Vf square by t, whereas in linear case I require multiplied by of course m Vf square by t multiplied by m. So, I actually require less power. So, very often the vehicle may be power constrained. So, if the vehicle is power constrained, motor is power constrained, you do not want to go at a constant acceleration. You may want to accelerate in the beginning more and then slow down. On the other hand, there may be cases where you may where a peak power requirement is not there, you can actually do something like this. This actually is given in assignment number 1.2. This problem is actually given. When you solve this for this, you will actually be able to determine this. So, I just wanted to point this out and leave it out here. So, what is the average power required for acceleration and what is the peak power required for acceleration? If I take a two-wheeler and suppose I want to reach only 25 km/h in 20 seconds, 25 km/h is 6.95 meters per second. I calculate my force required is 66 newtons, my torque requirement is 18.5 Newton meter. This is due to acceleration alone, I have not taken other forces. Average power requirement is 228 watt, peak power requirement is 458 watts. As I pointed out, that it is possible to reduce peak power by first accelerating faster and then slower down. At 50 kilometer instead of 25 kilometer, suppose in 20 seconds I want to reach 50 kilometer, torque requirement will go up to 37 Newton meter and peak power requirement will go up to 1.83 kilowatt. So, this is the difference between a two-wheeler which goes to 25 kilometer versus 50 kilometers per hour. So, your motor requirement will become much bigger, battery requirement will become much bigger. And note that this is due to acceleration alone. We will require to also overcome the other resistances like rolling resistance and aerodynamic resistance. Similarly, you compute for e-rickshaw. E-rickshaw the force is much more, because you have a weight of 680 instead of a weight of 190. So, the force required is 236 Newton and therefore, torque requirement is 47 Newton meter. Average power requirement due to this acceleration is 1.64 kilowatt, sorry 820 watt, but the peak power requirement is 1.64 kilowatt. At 50 kilometer, now e-rickshaw does not travel at 50 kilometer per hour, but if it were allowed to travel, our peak power requirement would have gone up to 6.5 kilowatt. And I do the same thing for a car. Car at 50 kilometer per hour or 13.9 meters per second, let us say in the same 20 second, my force requirement is now 833 Newton meter, but look at my torque requirement is 258 Newton meter. This is due to acceleration alone. Remember, for the car, even for climbing, the torque requirement was very large. So, we have to put all these things together, and generally you will not be able to, your motor will not be able to handle this. So, you will require an appropriate gear. We will talk about gears also in this course as we go on. Average power requirement to accelerate is 6 kilowatt, not that bad. Peak power requirement is 12 kilowatt. And this is at 50 kilometer. If I went to 70 kilometer, my peak power requirement is going to go to 23 kilowatt, and if I went to 90 kilometer per hour, my peak power requirement will go to 37 kilowatt. So, if you see, if I go higher and higher speed, and I still want to accelerate in 20 seconds, my power requirement will go higher and higher and higher. And generally, of course, you do not go to this higher peak power, because you accelerate faster in the beginning and then slower, and that can probably bring it down to 18.7 kilowatt. So, the point that I am making is there is a fairly large requirement for power and torque due to acceleration. We will be putting that together, but remember, we will again talk about what happens when climbing down. Well, climbing down we will gain some energy, maybe or whatever deceleration, instead of acceleration, if deceleration, I will gain some energy. Maybe I will only gain 30% of that energy. So, but the effective energy used becomes smaller, energy used smaller, power used is not smaller, because remember, power is used at the time of acceleration. You also use that much energy, except you recover back that energy during deceleration. Okay. So, this is what we will do, and there are 3 assignment problems that I have defined. By now, I think we have done enough for you, and this is our little bit tedious assignment. You have to actually do the work for the 3 vehicles, 2-wheeler, 3-wheeler and 4-wheeler that were defined in assignment number 2.1. Compute total traction power assuming pickup speed from 0 to 50 kilometer per hour. We had in 20 seconds, we had already computed the rolling resistance and the aerodynamic resistance. You also compute the power and torque at 30 kilometer, 50 kilometer and 80 kilometer, assuming linear acceleration and 0 slope. Another problem, assume vehicle acceleration is some value in the first 10 seconds and half as much over the next 10 seconds to still reach 50 kilometer per hour in 20 seconds. Now, again compute the traction force, power and torque, and this actually problem number C is what you need to do before B, because this will give you the kind of expression that you will require to compute that. So, these are the 3 problems that I would like you to do, and I think we have pretty much learned the individual forces, the rolling resistance, the aerodynamic resistance, the gradient resistance and acceleration. We have learned forces required, we have learned the torques required, we have learned the power required, and to some extent we have talked about energy required, including the regeneration. But you know, these are number of computations that you did individually, your mind would be very confused. You still do not have a total picture. What do these numbers mean? So, in my next section, I am going to put it all together Instead of doing it in pieces, we will put it together and then try to compute what does it really mean, what does each kind of vehicle will imply, and we will do